In today's lesson, we're going to learn how to solve for a variable. When the problem asks you to solve for a variable, that means that you are expected to isolate that variable. For example, in problem number 1, we're asked to solve for y. That means that we are supposed to isolate y. Our final answer should be in the form y equals some expression. For this first problem here, there are multiple different ways you could solve it. I'll show you two different approaches we could use. Method 1 is consistent with an approach that we were learning earlier on in this chapter. We learned that if you have an equation that involves fractions, you can get rid of those fractions by multiplying each and every term by the LCD. And just for clarity, I often like to write the LCD as the LCD over 1. So to start, let's identify the least common denominator. The denominators here are 3, 2, and the implied denominator here is a 1. So the least common denominator, in other words, the number that 3, 2, and 1 all multiply into, would be 6. So let's go ahead and multiply each term by the LCD over 1, or 6 over 1. We'll multiply 6 over 1 by the 2/3 x. Then we'll multiply the negative 5/2 y by 6 over 1, and then we'll multiply the 5 by the LCD over 1. Again, with equations, in order to maintain equality, whatever you do to one side, you have to do to the other side. So that's why we have to multiply each and every term by the LCD over 1. This will get rid of our fractions completely. Now let's do some canceling here. Let's see. We can take 6 divided by 3 to give us 2. And then we're left with the 2 times the 2x to give us 4x. And in the denominator, we only have a 1, so we don't need to write it. We can cancel over here. 6 divided by 2 gives us 3, and we'll be left with negative 3 times 5y to give us negative 15y. And then we're just left with 1 in the denominator, so we don't need to write it. And then over here, we're left with 6 times 5, which will give us 30. This LCD approach is nice because it totally gets rid of your fractions, and equations without fractions are often easier to solve. Now the goal of this problem is to solve for y. That means we want to isolate y. We want y all by itself. So let's start by subtracting away this 4x. And if we subtract it from the left side, we have to subtract it from the right side. That will leave us with negative 15y is equal to, and you can write this as 30 minus 4x, or you could write it as negative 4x plus 30. Now we've almost solved for y. In other words, we've almost isolated y. The last step is we need to get rid of this coefficient, the negative 15. So since y is being multiplied by negative 15, let's do the opposite. Let's divide by negative 15. And what we do to one side, we have to do to the other side. You could either write this whole side is over negative 15, or we can divide each individual term by negative 15. And I'm going to use that approach because often it's a little bit easier to simplify that way. These negative 15s cancel, and we're left with y is equal to negative 4 divided by negative 15. The negatives cancel, so we're just left with positive 4/15. And this fraction does not reduce any further. And then 30 divided by negative 15 gives us a negative 2. Now we've completed the problem because the problem asked us to solve for y, and we have isolated y. Notice here we have 4/15 x. You can either write it like this, with the 4/15 as the coefficient and the x out front, or we could also write the x in the numerator like this. Both of these are equivalent and both of them are correct. Let's take a look at another approach. So in method 1, we got rid of the fractions by multiplying each term by the LCD. In method 2, you see a slightly different approach here. I've started by just copying down the original problem. Now we want to solve for y. Let's start by getting rid of this 2/3 x. Let's subtract 2/3 x. And if we subtract it from the left, we have to subtract it from the right. This will leave us with negative 5/2 y is equal to, and we can write this as 5 minus 2/3 x, or negative 2/3 x plus 5. Now, in order to isolate y, we have to get rid of this coefficient, the negative 5/2. There's two ways we can do this. The first way, since y is being multiplied by negative 5 halves, we could do the opposite and we could divide by negative 5 halves. And if we divide this side by negative 5 halves, we can either divide this whole other side by negative 5 halves, or what I like to do is to divide each individual term by negative 5 halves because it's often a little bit easier to simplify that way. Now we could do this, especially if you have a calculator. Just dividing these fractions and dividing this is pretty quick using a calculator. But even using a calculator, if you type it in incorrectly, you could get the wrong answer here. And if you do this by hand, when you divide by a fraction, you would have to flip and multiply. So I'm going to erase this step to show you a different approach. Okay, so I've erased that. Now we still need to get rid of this coefficient. If you have a coefficient that's a fraction, if you want to get rid of it, instead of dividing by it, another option is you can multiply by the reciprocal of that fraction, which just means you flip it. So if we flip negative 5 halves, that leaves us with negative 2/5. What you do to one side of a fraction, you also have to do to the other side. And if we multiply this left side by negative 2/5, you can either multiply this whole other side by negative 2/5, or as I like to write it, let's multiply each term by negative 2/5. Okay, so I've multiplied the negative 2/3 x by the negative 2/5 and the 5 by the negative 2/5. Now notice, if we had used the first approach that I erased, dividing by a fraction, whenever you divide by a fraction, you have to flip and multiply. And that's what we just did. We just flipped and multiplied anyway. But the reason multiplying by the reciprocal helps us to isolate y is because what happens when you multiply two reciprocals? When you multiply two reciprocals, you get 1. So we're left with 1y. Let's see. Negative 2 times negative 2 will give us a positive 4. 5 times 3 will give us 15. And then we can put the x either out front, or if we want to put it in the numerator, we could do that as well. And then let's see, we can picture this 5 as 5 over 1. And so this would give us negative 10. And if we multiply the denominators, that'll give us 5. Now if we simplify, 1y is just y. 4/15 does not reduce any further. And negative 10 divided by 5 gives us a negative 2. So we see, even though we used a slightly different approach in method 2, we get the same answer that we did using method 1. Let's take a look at another problem. Problem number 2 is a very widely used formula. It's actually the formula for converting between Celsius and Fahrenheit. So as this formula is written, if you know a Fahrenheit temperature, you can plug that Fahrenheit temperature into the formula, and then you can compute the corresponding Celsius temperature. But what if instead you know the Celsius temperature and you want to convert that temperature to Fahrenheit? You have to rewrite this formula so that it's solved for Fahrenheit. And that's exactly what we're going to do here. We're going to solve for F, or Fahrenheit. There's several different approaches we could use here. I'm not going to go through all of them. I'm going to show you just method 1 here. So method 1 says, if you have an equation and you notice that you have fractions, you can just go ahead and get rid of those fractions by multiplying both sides by the LCD. So what is the least common denominator in this case? Well, let's see what all of the denominators are. Well, the c we could just write as c over 1. The denominator here is just a 1. What about over here? As a side note, we could rewrite this expression here as 5 times f minus 32 over 9. These represent the same quantity. If we write it this way, though, it's a little bit clearer to see that the denominator here is a 9. So since the only denominators we're dealing with here are a 1 and a 9, our least common denominator would be 9. So we're going to multiply each side of the equation by 9, or 9 over 1 as I like to write it. So I'm multiplying the c by the LCD over 1, 9 over 1. And then we want to multiply this expression here by the LCD over 1, 9 over 1. Now over here, we just have 9 times c, which gives us 9c. Over here, these 9's cancel, and so we're just left with 5 over 1, or in other words, 5, times f minus 32. We see that with equations, whenever you multiply by the LCD, you get rid of the fractions, which we've done here. The next step is, let's see, we're trying to solve for f. So we want to isolate f. There's a few different approaches you could take here. You could distribute the 5 and proceed to solve that way, and that would work. You'd get to the correct answer in the end. Another thing we could do, instead of distributing the 5, we could go ahead and divide by the 5. Let's take that approach. So I'm going to divide this side by 5, and then we'll divide the other side by 5. That will leave us with 9/5 c is equal to, these 5's cancel, and we'll just be left with f minus 32. Now we're trying to solve for f. We've almost solved for or isolated f. The last step is we want to get rid of this minus 32. So let's add 32 to the right, and then we have to add 32 to the left. And that will leave us with 9/5 c plus 32 is equal to f. Now we've solved for f. We've isolated f. The last step is that generally when you solve for a variable, it's standard practice to write the equation with the variable on the left. So let's just swing this around the equal sign and rewrite our final answer as f is equal to, we put the isolated variable on the left, 9/5 c plus 32. Now this was just one approach. You could have instead, for example, in the beginning, if you wanted to distribute the 5/9 and solve that way, that would have worked as well. There's multiple different ways we could solve this. Now, if I'm teaching this lesson in person, I always ask my students to pause for a second and attempt problem 3 on their own. If you're watching this video, I encourage you to pause the video and try this problem on your own. A very common incorrect way to solve this problem is a student will say, okay, we're supposed to isolate or solve for p, so they will add PRS to the right side, and then they'll add PRS to the left side, and then they'll be left with z plus PRS is equal to, these PRS's cancel, and we'll just be left with p on the right. Now it looks like we have solved for or isolated p, but this answer is incorrect. We have not solved for p because p appears on two different sides of the equal sign. When you solve for a variable, it should appear only once on one side of the equal sign. It should not appear twice like this on two different sides of the equal sign. So how do we correctly solve this? Let's compare this problem to the previous problems. In this problem here, we were trying to solve for y. Notice in the original problem, y appears only in one term. In this problem here, we were trying to solve for f. Notice that f appeared in only one term. It didn't appear more than once in the problem. In this problem, we're trying to solve for p, but notice that p appears in two different terms. If the variable you're trying to solve for appears in more than one term in your original problem, you're going to have to factor out that variable. So just a quick review of factoring. When you're factoring, you want to look for the greatest common factor between your terms. So here, if we consider these two terms, the greatest common factor is 4. So to factor this, we would factor out the 4, and then we would say, okay, 4 times what gives us 4? Well, 4 times 1 gives us our 4. And then we ask ourselves, 4 times what gives us our negative 4RS? Well, 4 times negative RS gives us our negative 4RS. Whenever you're factoring, you can always check your work by distributing and making sure you get back to your original problem. So let's see, if we took the 4 times the 1, we would get 4. And if you take 4 times negative RS, we get negative 4RS. Let's try to factor a similar problem. Let's factor the problem P minus PRS. Notice these are the same problem. The only difference is I've replaced the 4's with P's. So when you're factoring, the first step is to check for a greatest common factor. The greatest common factor here was a 4, so we put a 4 outside of the parentheses. The greatest common factor here is a p, so we put a p outside of the parentheses. Then we ask ourselves, if we were to distribute, p times what gives us p? Well, p times 1 gives us p. And then if we were to distribute, p times what gives us negative PRS? P times negative RS gives us our negative PRS. So if we look back at the original problem, we said if you're trying to solve for a variable, if that variable appears in more than one term, you're going to have to factor out that variable. So we needed to factor out p, and that's exactly what we did right here. So we took this problem and we factored out the p. So I'm just going to copy the factored form right here. P times 1 minus rs. And then we'll just bring down the z. So this is equivalent. We could get back to the original problem by just distributing the p. Now, why does that help? Well, we're trying to isolate p. Now, we can isolate p very quickly by getting rid of this quantity right here. P is being multiplied by this quantity, so let's divide by the quantity 1 minus rs, and then we can divide the other side by that quantity. That will leave us with z divided by 1 minus rs is equal to, these will cancel, and we'll just be left with p on the right. So we've succeeded. We've isolated p. The last step is we typically like to write our isolated variable on the left. So let's just swing this around the equal sign and write this as p is equal to z divided by 1 minus rs. The last problem gives us the formula for calculating the volume of a right circular cylinder, which is the shape we see right here. Now this formula here has the v isolated. So we could plug in the radius and the height and then compute the corresponding volume of the right circular cylinder. But let's suppose we wanted, for example, to compute the height of our cylinder. Well, then we would have to rewrite the formula so that we've solved for h. In other words, so that h is isolated. Or let's suppose we wanted to calculate the radius. Well, then we'd have to rewrite our formula so that we've solved for r. And we're going to practice that here. So here we want to solve the formula for h. So I've started by copying down the original given formula. Now if we want to solve for h, that means we need to isolate h. So right now, h is being multiplied by pi and by r squared. So the opposite of multiplying by pi and r squared would be to divide by pi and r squared. And if we divide the right side by pi r squared, we have to divide the left side by pi r squared. Let's see, on the left we'll be left with v divided by pi r squared. And on the right side, the pi's will cancel and the r squares will cancel, and we'll just be left with h. So we've successfully solved for h. For our final answer, let's rewrite this with h on the left, so we can write it as h is equal to v divided by pi r squared. Be careful when you write your final answer for problems like these. If in the original problem the v is capitalized, make sure you capitalize it in your final answer. Here the r and the h are lowercase, so we've written the r and the h as lowercase letters in our final answer. Let's take a look at a sample problem here. Tasha's family just bought a cylindrical hot tub. The hot tub company told Tasha that the tub holds 40 pi cubic feet of water. Tasha is interested to know how deep the tub is. She measures the diameter of the top and finds that the hot tub is 6 feet across. What is the height, in other words, the depth of the hot tub? Round to 2 decimal places. So what is this question asking for? The height of the hot tub. And since we're dealing with a cylindrical shape, we can use this formula here, or this one. And since we want to compute the height, we want to use this formula here where the h has been solved for. So I went ahead and copied down this formula over here. We can start by plugging in the volume. Volume is typically given in cubic units. And we see in the problem we're told that the tub holds 40 pi cubic feet. So that's the volume. So I plugged in 40 pi for v into the formula. And now we want to plug in the radius. We're told that the diameter is 6 feet. The radius is always half the diameter. So if the diameter is 6 feet, the radius would be half of that, or 3 feet. So I plugged in 3 for the radius. Now let's go ahead and simplify. To start, since there's a pi in the numerator and a pi in the denominator, we can cancel those pi's. Next, let's go ahead and compute 3 squared, which gives us 9. So we're left with 40 over 9. And the problem asks us to round our answer to 2 decimal places, so that means we want to convert this to a decimal. To do that on your calculator, you could just go ahead and take 40 divided by 9, which rounded to 2 decimal places leaves us with 4.44. And let's include units. Since it looks like the units in the problem are feet, we can say that the height or the depth of the hot tub would be 4.44 feet.